Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is Lecture 11. I want to first remind you what we did in Lecture 10. And it was essentially one idea, which is we wanted to express linearity of expectation. So this is a quick recap of Lecture 10. So linearity of expectation. This says that, first of all, not only is there a notion of a sum of two random variables, but I can also do things like scale each of the random variables. And once you accept those two ideas, we have the following beautiful formula, which is that if I look at the expectation of ax plus by, which again is a random variable that comes from first picking a random number according to x, then picking a random number according to y, scaling the number of x by a, and then scaling the number produced by y by b, and then adding the result. Now, computing the probability distribution for ax plus by can be a little complicated. And again, something we'll be considering as we move throughout this course. But remarkably, the expectation is very simple and doesn't even require us to compute anything new, assuming we already know what the expectation of x is and the expectation of y. Today, we're going to go a little bit deeper into this idea of a joint random distribution, where I want to study how possibly two or more random variables need to vary together. So we're going to continue this idea, or maybe we'll say the study of joint PMFs for two or more random variables. And we're going to look at some big principles that come out of these case studies, but I really want to focus on examples. So let's just dive right into it. So let's imagine I draw two cards from a 52 card deck. So your standard card deck you play poker with. Now again, this is an experiment. And associated to this experiment, we can study one or more quantities. Let's say we want to study x, which is the number of queens in your two cards. And let's say y is the number of kings among the two cards. So the first thing you need to do when you have a pair of random variables is you need to start asking some basic questions like, how do these vary together? And this is all encompassed by studying the Joint Pmf, which essentially just records the and probabilities for each possible outcome of the two random variables. So let's do this. So let's write down the probability mass function associated to x and y, which we would interpret as writing down the probability that big X equals little x and big Y equals little y across all possible values for little x and little y. Of course, in this situation, things are kind of nice. We're only drawing two cards. And in particular, you can't have both two queens and two kings. There's some sort of exclusion that happens. So let's go ahead and just sort of write this out. In this setting, it's probably simplest just to do the calculation directly. So let's first compute probability of no queens and no kings. So just take a moment to think about how you might approach that. Well, the observation is if I'm drawing neither a king nor a queen, then I need to remove the 8 cards that represent kings or queens. So that means that we have 44 non-king or queen cards. And the probability that you draw 2 of these non-king or queen cards is pretty simply, well, you have 44 cards of that type, you choose 2 of them, and then you need to divide by all possible 2 pair drawn from a 52 card deck, or I should say single pair, just 2 cards. So that's probability of 0, 0. So if I were to start filling out my table, this would be one of the first entries I could get at. Let's go ahead and compute the probability of 1 queen and 0 kings. So again, following the same basic idea, I have 4 queens to choose from. I choose one of them, and then I need to choose one of the remaining non-queen or king cards. We just determined there are 44 of them. So that gives us 44, choose 1. Again, divided by 52, choose 2. Now, if we think about it a little bit, this is also equal to probability of 0, 1 by symmetry. I could have just relabeled the queens in my card, in my deck of cards, kings, and repeat the same calculation. There wouldn't have been any difference. So I've now already computed 3 of the possible values for my joint PMF. Let's go ahead and compute the last one, which is this idea, well, the last couple here. So here we've already done this one, and then this one. Now let's go ahead and compute probability of two queens and 0 kings. Again, fairly straightforward. There are 4 queens. We need to choose 2 of them, and then we divide that by the total number of 2-card pair, 2 cards drawn from a 2-card deck. And again, by symmetry, we know that this is the same thing as probability of 0 queens and 2 kings. And so now we're left with the sort of last quantity of interest, which is what's the probability of 1 queen and 1 king? And again, we choose one of the queens, we choose one of the kings, and then we divide by the space of possible 2-card draws from our 52-card deck. And that's it. This completely determines the PMF of these 2 joint random variables. So let's go ahead and tabulate some of these values, and I'm going to write them down using approximate percentages, just so we have a good idea of what these numbers look like. So again, if we write down my joint probability table, it's going to look a little something like this. So I've got my number of queens, and I got Y here being my number of kings, and 0, 1, and 2 are possible values for each one of these. But then I also see that there are certain joint values that are not possible. For example, as I said earlier, you can't have 2 kings and 2 queens because we're only drawing 2 cards. Similarly, I can't have 2 and 1, or 1 and 1, or 2 or 1 and 2. So I can immediately write in 0 for these. Now, the other calculations we just did, well, let's see. We had 2 and 0, which was this whole 4 choose 2 divided by 52, 52. If you do that math, it works out to roughly about 0.5%. I'm just going to write this as something that's less than 1%. And by symmetry, we know that this is also less than 1%. For this value of 1 and 1, it's a little more than 1%. And then I'm just going to go ahead and write down these values here. So if you just double check my math, see these are about 13%. Again, a little more than 13%. So this is about 13% by symmetry. And this is 71%, a little more than 71%. So again, by and large, maybe it doesn't seem too surprising that if you draw 2 cards from a 52 card deck, most of the time, you're not going to get either a king or a queen. That's why we like those cards. But again, the fact that we rank them higher is sort of artificial. It just happen to be 2 out of the 13 possible face values. All right, so I want to observe a couple things. So here's some important properties to observe. So observe. So the first property is that this joint probability mass function is itself a probability mass function, but where my outcome space sort of naturally splits as a product of the 2 possible values, the number of kings and the number of queens, respectively. And again, you remember from basic probability theory early on, we had this thing called the normalization axiom. Which says that if I look at the sum over all possible values x and y of my joint Pmf, that has to equal 1. And we kind of see that happening here. So here I have 71%. Here's our little example, plus 26%. I can do that math, and then let's call that roughly 3%. And yeah, so 71 plus 3 gives me 74. Add the 26, that equals 100%. All right, great. Now, there's another really, really important property. And this is sometimes called the marginalization property. So, and I'll even call it an axiom because it follows from basically just the fact that you can always decompose your space and your probability space or your outcome space in a nice way, where again this sort of normalization property has to happen. Really, this is just an expression of the law of total probability. And it says this, and the reason why it's called marginalization is that I can marginalize, meaning right in the margins, the probability distribution for x and for y separately, just by summing everything that occurs in either the columns or rows, depending on which margin I'm looking at. So for example, if I'm looking at the PMF for x, if I want a probability distribution for x, I can get this. So 1 plus 13 plus 71, I think that works out to about 85. And then this guy gives me 14%. And again, here what I'm doing is I'm just summing this way. So I add this and this and this, and I get this number. Similarly here, 1 and 13 gives me 14, and this gives me 1%. And notice that this is itself also a probability distribution but now just on the number of queens. And you can actually check just via counting that this number is approximately correct. And then similarly, we get the same thing when we marginalize in the y direction. So if I take 71 plus 13 plus 1, I get the same result. So I get now I'm writing the PMF for y, 85%, get 14%, and I get 1%. So just to write this down right here, so here I've got that if I sum over all my possibilities, I have to equal 1, but I also have the property that if I sum over all possible values for y with fixed x, then I get the probability of x. So this is going to look something like this. So probability of PMF for little x can be computed by summing over all y of the probability of little x, little y. So this says that the PMF for x is equal to the restricted sum of the joint Pmf. And also by symmetry, of course, the probability mass function for y can be obtained by marginalizing, meaning writing in the margins, the probability mass function that comes from the joint, and by just summing over each of these. So there's a lot of good reason to then study these joint probability mass functions, because we can obtain separately then the probability mass functions for both x and y. This is an important point to then note the definition of independence, which I kind of skirted over last lecture, and I want to state more clearly here. So here's this notion of independence. All right, so here's the definition. So we say that x and y are independent random variables if the probability, the joint probability mass function for x and y can be obtained just by taking the product of the probability mass functions for x times the probability mass function of y across those x and y. So now again, this is not always true. Again, so it's not always true. Yeah, so this is not an axiom. It's a property which we can check when we want to see whether or not two events or two random variables are independent or not. Now, one thing I want you to notice in this case is that if the probability mass functions for x and y are both non-zero for a certain pair of values x and y, then this necessarily implies that the joint probability mass function has to be non-zero for those. And in this case, we actually see that that's totally wrong. So notice here I've got probability that x equals 2 is 1%. The probability that y equals 2 is also 1%. So if x and y were independent, then I would say that probability that x equals 2, y equals 2 is 1% times 1%. But that's not 0. And I obviously know that if I'm only picking 2 cards out of a deck, I can't have 2 queens and 2 kings. So the fact that the support, and by support I mean the set of values that are non-zero, isn't the sort of product of the supports of X and Y automatically tells me that these things are not independent. So let me just go ahead and write that here. So bene X and Y are not independent. All right, cool. Okay, so that was a nice sort of warm-up calculation, and maybe just to sort of stress that this marginalization axiom in the case of my choosing 2 cards and getting 2 queens, we could just check. So what's the probability of no queens? Let me just do this real quick. Probability of X equals 0, so it's no queens. Well, I need to take 2 out of my non-queen cards, so it's 48 choose 2, divided by 52 choose 2. And if you go ahead and compute this, you'll see that this is actually indeed about 85%, which is what we got by summing across all the possibilities of, oh, was maybe one of those other cards a king or not. That's information we didn't care about by doing this calculation, but we did care about when doing this one. And but nevertheless, having extra information means that you can always combine that extra information to then get the setting where you had less information. All right, so again, 3 big concepts here so far is we have the normalization axiom for joint PMFs, we have the marginalization axiom, and then we also now have our definition of independence. And you could generalize this definition where you have, let's say, 3 random variables. But you might ask, what is such a setting where we have 3 random variables? So that motivates the next example. All right, so here's an example of 3 random variables. All right, so it's not something we've done yet. So far, we've only been concentrating on basically 1 or 2 random variables. But nevertheless, there are sort of easy variations on problems. We've already seen some before where this actually kind of makes sense. So let's imagine again that we've got our urn. And we've got 2 red balls. We've got 2 green balls. And we've got 2 blue balls. All right, so, and just like we were doing with the deck of cards, let's imagine that we draw 2 balls out. And in this case, we don't really say, we should assume that we're drawing the 2 balls out without replacement. So I'm reaching in and grabbing 2, which is the same thing as picking out 1 and then picking out another, but not remembering which one was first, which one was second. All right, so we've got urn with 2 red balls, 2 green balls, and 2 blue balls. I'm going to draw 2 out. That's our experiment, and we want to be able to understand the space of possible outcomes for this experiment. And of course, I'm being obsessive here. Let's go with 2 red balls here. Very good. All right, so you might ask yourself, if I asked you how to write down the joint PMF for the number of red balls, green balls, or blue balls in a draw, because again, when I draw 2, I can get 2 a different color, but also the space of colors is something of interest. It's sort of multivariate. So here's the question: how do we visualize the PMF of RDG, which counts the number of red, the number of blue, and the number of green balls? This is a sort of an example of like a three-dimensional PMF. So maybe in your mind, you could start imagining, well, how would I even start to picture this? Well, I've got three axes of interest. Let's say that the sort of end of the page axis is the number of red balls, and then I've got the number of blue balls as my y-axis, and number of green balls is my x-axis. And then, you know, of course, I've got sort of 0, 1, 2, 0, 1, 2, 0, 1, 2 as these sort of possible values. And so somehow I need to kind of slice my cake or my bread loaf here, and maybe do this PMF table one at a time, which is exactly what I'm going to recommend we do. So let's go ahead and look at this first slice. Let's go ahead and pull out this first slice. So here we're going to fix r equals 0. And now we're going to look at the probability table associated with the number of blue balls and the number of green balls, which again, we know 0, 1, 2, 0, 1, 2 are our possibilities here. And so now I need to figure out how to fill in this table. All right, so again, first thing you want to do is start eliminating possibilities, things that you can just eliminate by pure logic. Well, obviously, if I'm drawing 2 and I'm capturing all possibilities, I can't get 0 green balls and 0 blue balls and 0 red balls. It's just not possible. Similarly, any of these numbers which add up to more than 3, I can eliminate. But I can, and I can also eliminate this in this case. So, oh, sorry, no, not that case. Sorry, that makes good sense. But these other ones I can. So I could have 0 here. There we go. Yeah, that looks right. So now let's just go ahead and figure out, well, what is the probability of getting 2 blue balls, 0 green, and 0 red? Well, it's kind of like the card setup here, right? So I've got 2 blue balls. I'm going to choose 2 of them. I need to divide this by the space of 2 ball draws. It's 6 choose 2. And then similarly, by symmetry over here, I could say that this is also 2 choose 2 over 6 choose 2. And so just remember that this this ends up being 1 over 6 choose 2, which, if you think about it, ends up being 2 times 6 times 5, which is 1/15. So each of these sort of extreme points end up having a 1 out of 15 probability. Now, what about this setting here where we're looking at the number of blue balls being 1 and the number of green balls being 1? Here's a little more hope, because I could choose 1 of the blue, choose 1 of the green, and there's 2 choose 1 ways of doing each of those things. So I have 2 times 2 in the numerator, and still my 6 choose 2 in the denominator. And we can kind of keep filling this out here. So so again, just this is 1 over 15th, and then this guy here has to be a 4 out of 15. There, so I'm starting to carve out my space of possibilities. I've already gotten 6 out of the 15 space of possibilities, assuming the normalization axiom is true, but it has to be. If it's not, if your numbers don't add up to 1, then you've done something wrong. All right, and so now let's look at the second slice here. So fix r equals 1, 0, 1, 2, 0, 2. So we can't have that. We can't have this. Can't have either of those being 2. I could have 1 and 0, but I can't have this, and I can't have this. And I also can't have this. So I got two possibilities here. And what does that work out to be? Well, so probability of 1 red and 1, let's say, again, this is the blue axis and this is the green axis. Well, if you think about it, that shouldn't be any different than the probability of getting your situation here, where you had probability of 1 blue and 1 green. Now you're just saying 1 blue and 1 red. So if you believe that logic, then let me use this slightly smaller here. So then we end up having 4/15 over here and 4/15 over here, which again just comes from 2 choose 1, 2 choose 1 over 6 choose 2. All right. So where are we at so far? So we've already accounted for 6/15. Now we have 8/15, and this bodes well because we've got one more slice to consider, and that's the slice where r equals 2. Again, if you try to visualize what this looks like, got a number of blue balls here, a number of green balls here. All of these have to be 0. And we kind of see that there's this interesting kind of cutting through this plane which goes through my cube, and as I'm stepping through, I'm either intersecting along this sort of diagonal, or then the one right below the diagonal. So this being the diagonal, and then when I move over, now I'm slicing here, and then trying to slice here. So that's sort of a fun thing to visualize in this cube of possibilities. But anyhow, what's the probability here of 0 blue and 0 green? Well, it's the same thing as sort of assuming I've only chose, I did my 2 choose 2, and then 6 choose 2. So that ends up being my 1 out of 15 again. Because again, I've got my 2 red balls, I have to choose both of them. There's only one way of doing that out of my 6 choose 2 total number of possibilities. And so hopefully you feel right with all those calculations, but I will tell you that there are multiple ways to compute these numbers. And you can think of this both as the beauty of probability, or you can also think of it as the sort of curse of probability. There's not one way to do this. So let me mention 2 alternative ways that also reveal interesting properties. So you could have also done, also have what's called the multiplication rule. Which says that, if I ever want to know the probability of, let's say, x equaling x, little x, and capital Y equaling little y, then I could also use this conditional that says the probability of, let's say, x equaling little x, assuming y equals little y, and then I multiply that by probability of y equaling little y. So again, this is sort of an aside here. I'll just give this a little hole in the clouds to pass through. It doesn't actually use it. At least not here or there. We just sort of did a brute force calculation. Now, of course, you can imagine there's a three-dimensional version of this rule. And let's go ahead and figure it out. So, I computed here that the probability of red equaling 1, green equaling 0, and blue equaling 1. I could have also computed this as the probability of green equaling 0, blue, the number of greens being 0, number of blue being 1, assuming that the number of reds was equal to 1, and then multiply this by probability of having one red ball. Well, let's see. How does this make things any easier? Well, maybe. So I'm imagining I've already removed a red ball, and I know I'm not going to pick any other red balls. So I'm now in the situation where I've got 4 balls in contention, my 2 green and my 2 blue, and I have to choose one of the blue. So just to write this out in words, so let's remove red balls. It means we have 4 left. Now let's compute probability of 1 blue. Well, by my lights, that looks like I've got 2 choose 1 out of my 4 choose 1 possibilities, which ends up being 50%, right? 2 over 4. Now, what is the probability here of getting 1 red ball? And this is sort of the total probability here. Well, you can think about it also using the kind of thinking we do for counting hands in a poker game, where I've got 2 red balls and I need to choose one of them. And then I have 4 other balls and I need to choose one of those. So that gives me 2 choose 1. And then I have 4 choose 1. And then I'm dividing this all by 6 choose 2, because again, I'm choosing my 6 possibilities here. So that's that. And then this is this. But notice we've got some nice cancellations. And indeed, we end up getting the answer that we sort of expected, which is 2 choose 1, 2 choose 1, divided by 6 choose 2. And again, that's that agrees with, let's see, R equals 1, B equals 1. That's exactly this right here. So we could have. That's another way of calculating that. Now, again, if all of this is sort of too much to keep in your head, you could always go back to basics. What does basics look like here? Again, probably one of the most useful tools and that you'll get in discrete probability, which is, so here's the third way, which is just considering the tree of possibilities. Well, so imagine I've got my urn with 6 balls. I draw my first one. This is my first draw, and I've got a 1/3 possibility of each of these. And then again, I've got red, green, blue, red, green, blue. Now, the one thing to keep in mind here is that the probabilities that I write on each of these edges is conditioned on what happened before. So in particular, if I draw out a blue ball in the first step, then the probability of getting a blue ball in my second step, well, let's think about it. So I've taken one out. So it means I've got 5 balls left, and only one of them is blue. So this looks like 1/5 by my calculations. But on the other hand, each of these other possibilities, assuming you're trying to pick one of the other colors, there's 2 of those other colors remaining. So each of these has 2/15. And so what this tells you is the ordered probability of each of these draws. So in particular, if I wanted to calculate probability of blue then red, this would be 1/3 times 2/15 is 2/5 is 2/15. That's this. Whereas this is probability of 2 blue. There's only one way of drawing 2 blue, which is to get a blue ball in the first draw and a blue ball in the second draw. And so that's this 1/15. But we also can observe this is the same thing as 1/6 choose 2. What happens when we forget order here? Other things we can do nicely here. So what's the probability of 1 red ball? Well, there's sort of 2 ways of doing that. So we've got, so here's one way, blue and red, or we could have red and blue, or we could have green and red. I believe that is it. And so what does that work out to be? This ends up equaling, if we sum this all up, well, where I saw this was 2/15. This is also 2/15. So summed all together, this ends up equaling something that looks like let's see. Right. Looks like 6/15. All right, let me just double check my calculations here. So, no, I'm missing one. Probably that red equals 1. Yeah, well, of course I could have also gotten red and green. So then this is also my, this is also 2/15. So my correction is the probability of 1 red ball equals 8/15, which is also the same thing as I have 2 red balls, I choose one of them, and then I have 4 other colored balls and I choose one of them. So both these calculations work out exactly the same way. All right. So this is sort of meant to be cumulative. Let's consider another variation on this problem. And obviously that was a little complicated because I had to consider, what happens on my first draw versus what happens on my second. Let's vary the question. Let's vary the example. So now let's do the sort of independent version. The earn example, which we know should sort of correspond to doing draws with replacement. Meaning, I pick a ball out, I look at its color, I put it back, and then I swirl around and I pick out another one. But I can still count the same number of same things, which is what was the number of red balls in this experiment, what were the number of greens, what was the number of blues. It turns out there's a really nice general formula that handles this, and it's something called the multinomial distribution. And we've already kind of considered this in the setting of assigning people to schools and also counting the number of permutations without being able to distinguish. So if we did, maybe you can sort of see why this multinomial distribution shows up here as well. All right, so it's a little too whimsical. All right, so what's the basic idea here? So if I have, suppose I have n independent trials with m possible outcomes. Now you might want to even think of this as sort of categories or colors. At each step. And if I define the random variable to be the number of trials whose outcome was I, again, we need to recognize that I ranges between 1 and m, then I can write down the joint Pmf of this all in one go. I don't need to do the kind of case analysis that I was just considering, which looks something like this. So the probability that big Ni equals little ni, or N1, sorry, big N2 like equals little n2, all the way down through big N, n, or m, sorry, yeah, because there are m possible outcomes, equals little n m. Again, these are the number that occur of a particular outcome. So you think of this like the number of color balls. It's going to look something like this. So it'll be n factorial divided by n sub 1 factorial on down through n sub m factorial times p1 to the m, p1 to the n1 up through pm to the nm, where p sub I equals the probability of outcome I. So let me just go ahead and put a big box around that. And let's go ahead and check what it would look like in our situation. So here, if we return to our example, so here's our example. I've got a urn with 2 red, 2 blue, 2 green, and then I do 2 draws with replacement. Then I can just sort of write down my table of what the possible values for R, which maybe you want to think of as n sub 1, B, which is n sub 2, and G, which is n sub 3. This is just the number of balls of color red or blue or green when I do these 2 draws with replacement. And again, that's where this sort of independence here is crucial, because I just multiply through. It's also nice because I know that P1 equals P2 equals P3. Each of them in this case is a third. I have a third of 2 out of 6 chance of getting a red, or 2 out of 6 get a blue, and so on. So let's just go ahead and figure it out. What are the possible sort of tuples here? So I could have 2 red, 0 blue, 0 green. I could also have, let's say 1 red, 1 blue, 0 green. I could have 0 red, 2 blue, 0 green. I could also have 1 red, 0 blue, 1 green. And let's see, also I've got my 0, 0, 2. Does that account for everything? Ah, no, there's one more possibility. So I could have 0, 1, 1. All right, now if we just apply the formula, it's going to look a little something like this. So let's now use my formula. So I should have 2 factorial over, well, 2 factorial, 0 factorial, 0 factorial. The 2's obviously going to cancel, and then I've also got 1/3 squared, 1/3 to the 0, 1/3 to the 0. But that just equals 1/9. Shows me the probability of getting 2 red balls is a 9th. Makes perfect sense. 1/3 chance of a red on the first, 1/3 chance red on the second. What about these other ones? So here I've got 2 factorial, 1 factorial, 1 factorial, times 1/3 times 1/3. So this is it's a little more interesting because I've got 2/9 here as the possibilities here, and of course this one's going to be a 9th just by similar reasoning here. This one's going to be 2/9, 1/9, 2/9. And let's just go ahead and make sure this all adds up. So I've got, let me add my 2/9 together. So that all together gives me 6/9, covers 2/3 of my possibility. And then conveniently, I've got these other 1/9 calculations. And so if I check and I sum these guys, then I get exactly what I should get by the normalization. So it is normal. By the normalization axiom. Cool. Let's do just one more sort of affiliated computation, because we had this question of marginalization. So I kind of gave you two parts here. So normalization, that's sort of normalization axiom was concept 1, and then marginalization. So let's check marginalization in this case. All right, so what does that mean in this case? I want to just figure out what's the PMF for red. So I just need to figure out what's the probability of getting a certain number of red balls for each of my 3 possibilities. Well, if I follow normalization, again, this says that I can just sum over my green and blue possibilities of this joint distribution, which is effectively what I've written in this table here, but I've just kind of like stacked them on right below each other instead of trying to do this sort of cube that I did earlier. So what does that mean in this case? Well, let's say I want to compute what's the probability that I get 2 red balls. Again, drawing with replacement. Well, I can see I've only got one way of that occurring, which I just computed was a 9th. So this ends up equaling 1/9. And then what about the probability of 2 red balls, or sorry, 1 red ball? Well, that corresponded to, here's an instance where I had 1 red ball. Here's another instance where I had 1 red ball. And so those are both purple. So I had 4/9 here. And then what about the probability of 0 red balls? well, let's go and inspect my table. Well, here's a 0, here's a 0, here's a 0 for a number of red balls. That's going to correspond to a ninth, and 2 ninths, which makes good sense, but that also gives me 4 ninths. So now the question is, could I have gotten this answer a different way? So if all I care about is counting the number of red balls drawn from an urn, where there's lots of different colors in there, and the draws are made with replacement, so each draw is independent. You could probably see that we can also check this answer with the binomial distribution. So what did that say? Well, here we think of our probability P, which equals our probability of success, equals probability of drawing a red ball. Well, as we already said, there are 2 out of the 6, so that's 1/3. And what's Q? So it's the probability of not red. That's also the same thing as probability of green or blue, which is 4/6, which is 2/3. And again, these two numbers add to 1. So, and then remember, for counting the number of successes out of in trials, I used my formula. My probability that big R equals little r is going to be, well, I could do n choose little r times p to the r and then q to the n minus r. In our case, this looks like, all right, let's see, probability that r equals 2. Given 2 draws, so I have 2 choose 2, this is 1, times 1/3 squared, which is 1/9. And then similarly, probability of r equals 1. Well, that's a little more interesting because one of the draws can be red and the other one's not red. So that's 1/3 times 2/3. And 2 choose 1 is just 2, so same thing as 4 ninths. And then finally, if I squeeze my calculation down here, so 0, well, that's 2 choose 0, that's 1. But then I have 2/3 squared, which turns out to be 4 ninths. So you can actually see how marginalization of a multinomial distribution onto a single axis, meaning single outcome, recovers the binomial distribution. That's not to say these things are independent, because again, this would say that the probability of red equaling 2, green equaling 2, and blue equaling 2 would be the product of all those, but it's obviously not the case because we're only drawing 2 balls. We're not getting 6 balls out. So that's just a connection with some older material. So I want to connect this back to what motivated us to even consider joint random variables, which was expectation. So let's compute a quantity here. So here's a question. So what is the expected number of red balls? And again, here we're drawing with replacement. Well, again, if we compute directly, expectation of R is going to be equal to, all right, well, 2 times the probability of red equaling 2 plus 1 times the probability of red equaling 1 plus 0 times the probability of red equaling 0. 0 times anything is 0, so we don't need to really worry about that. But then in this case, we have 2 times probability of red equaling 2 is a ninth. And then similarly over here, we had 4 ninths. So we add these things up, we get 6 ninths, which is 2/3. Now I want to show you another way in which we could have computed that. So here's another way. So this is the direct method. By definition method. Let's consider a slightly different method. So I could define what are called indicator random variables. So let me indicate the number of red balls by counting was the first ball that I drew out red, and then let me also have another random variable that says was the second ball I drew out red, and both of those can only have 0 or 1 as possible values. So if I call this, so now let me introduce the indicator method. So here I'm going to define R1 to equal 1 if the first ball was red, and 0 if the first ball is not red. So what's the probability the first ball is red? Well, we already know that this is a probability of this happening is 1/3, and the probability of this happening is 2/3, because 2 out of 6 of the balls are red and the remaining 4 are not. So I could define that, and I could also define R2 to equal 1, 0 if the second ball is red. And if you think about it, it maybe requires a little bit of convincing yourself, working it out the long way. But if I don't know any information about what happened in the first draw, the draws are independent, then again, I know this is 1/3. And then otherwise with probability Q being 2/3. And so then the observation is that, well, the number of red balls is the sum of these two indicators. And so if I use linearity of expectation, I can just say that, it's the same thing as the expectation of R1 plus the expectation of R2, which is 1/3 plus 1/3, which equals 2/3. And so now we've checked these 2 ways, 2 and 2. Now, let's go back to the original version of this problem where I did not replace between draws. And let's see if the answer is any different. So let's go back to draws without replacement. And so again, if we compute the expectation of R by definition, this expected number of red balls, well, let's see. So we had the probability of 2 red balls was a 15th, and the probability of 1 red ball was 8/15. And then plus a 0 times, the 6/15 of 0 red balls. But it doesn't matter what that is for expectation, because 0 times anything is 0. So what do we have here? We have 10 over 15, which also equals 2/3. And so I'm hoping you're kind of going, what? yeah, somehow, even though these experiments are very different, it turns out that the expectation here is the same. And I claim that we can see this by also using the indicator method. So if we use the indicator method, what would we say? We'd say, all right, well, R equals R1 plus R2. Now, what's the probability of the first ball being red? Well, it's 1 if first red. Well, we already know that that's a third. That makes good sense, and then 0 otherwise. Now, what about R2? So here I'm not replacing, but I also don't know what happened before. And so if you work out, well, what's the probability? First one's red, second one's red, and then what's the probability the first one's not red times probability the second one is red? You'll get that. This also is a third. So I would encourage you to check But remember, linearity of expectation worked regardless of independence. So it's then equal to E of R1 plus E of R2, which is also 2/3. All right, so that's the last sort of laborious calculation I want to do. But let me go ahead and summarize what we've discovered. So here are the two main upshots. Or methods. So, and this sometimes goes underneath the method of indicators. So the first one is this. So if I'm given an event A, which of course is a subset of my space of possibilities omega, and I define I of A to be essentially 1 if A occurs in my experiment and 0 otherwise, then the expectation of IA equals the probability of A. This kind of just also goes underneath the idea of like, well, I could define a Bernoulli random variable, 2 possible outcomes, 0 and 1. 1 with probability of success meaning A occurs, which is probability of A, and then 0 otherwise. But then this observation feeds into a more interesting or general method, which tells me this. So if I'm trying to count, so if X counts the number of occurrences of an event among A1 through let's say AN. So meaning of the events, let me just say it this way. Let me write this, of the events. A1 through AN, or can be used, I can decompose number of occurrences by counting whether each of these events occur. Then I have the following. So the expectation of X is the expectation of the sum of indicators functions, which by linearity equals the expectation of each of these IAJs, which by the above rule is the probability of each of these A1s through ANs. And again, this can add up to something more than one, which can be more than one. But the general idea here is, here I've got, let's say, 3 events, which is, let's say I roll a die and I want to say, I want to count the number of times the 6 comes up. So let's say, here's my example, X equals number of 6s out of 3 rolls. Well, I could let A1 be the event where the first roll is a 6. A2 equal the event that the second roll is a 6, and A3 equal the event that the third roll is a 6. And so if I do A1, A2, A3, but then I realize that each of these contributes a 1 to my sum. But if I'm in situations where both of these events occur, then I've got a 2. Or if I'm in the event where all 3 rolls are 6s, then that contributes to a 3. Of course, if none of these events occur, I get a 1. But it turns out this sort of linearity of expectation means that I can just compute the expected number of 6s. Of course, what does that end up being here? So if I want to compute expectation of X, well, what's the probability that the first roll is a 6? Well, there's only 1 out of 6, so I just sum these 3 times. So I end up getting 36, which is 1/2 is the expected number of 6s. All right, well, we're going to go through lots more examples in class, but I hope this makes sense, and I look forward to seeing you soon.